Good afternoon and welcome to the next lecture on computer vision. Last week, or in the last session, we discussed convolutional neural networks in depth. We saw how neural networks work, how to train them, and so forth, and how all of this works in a context of deep learning, as well as then convolutional neural networks that are particularly useful for vision problems. After that, we started with image sequence processing because we want to be able to process image sequences. We're not discussing this from a neural network perspective because those are things you would be seeing in a deep learning class or something like this. And computer vision is far more than just deep learning. So we're looking into other models that are extremely useful for vision. Particularly, we'll discuss the Kalman filter today, which is a very general approach. You can use it for far more than computer vision. And in order to understand the Kalman filter, we will be looking today again into temporal models, which we had started last week. We've looked into motion and tracking image sequences, and we looked at these three applications. And we will see they have a lot in common, in fact, today. And we will build the Kalman filter, and we discussed what filtering is. It allows us to estimate state variables from noisy observations over time. And we started with our temporal models, and we say we have the evidence, what we can observe, and we have our hidden state variables that we need to do inference about. And we work with time slices, and we had this example about the umbrella and rain. We looked at the Markov assumption, Markov processes, which is fundamental and we'll need it today. And we discussed also the sensor model before the transition model. And then we looked at that example in order to understand all of this a little better. I think there was a minor typo when I drew this figure on the iPad. I think there was a minus down here, should obviously be a plus because it's one time slice away. Since my drawings on the iPad are spontaneous, this may happen, but always refer to the figures in the slides, and because they are definitely fine. And we saw what these transition tables mean. For example, this transition table here means that the probability of an umbrella given rain is 0.9 when there is an umbrella, and when there is no umbrella, the probability of an umbrella is 0.2. Then we have this one, and which is 0.9, and the probability, therefore, of not having an umbrella when there is rain is 0.1, because 0.1 and 0.9 need to add up to 1. And the probability of not having an umbrella when there is no rain would be 0.8, because 0.8 and 0.2 need to add up to 1. So this is how you read these tables. Here, this table is fine too. However, this 0.7 and this 0.3 add up, but they don't necessarily have to, like we see here, because what needs to add up is the probability of having rain on a day when there is when there's rain before, as well as where you add this with the probability of not having rain that day. So the probability of not having rain given there was rain yesterday, that would be 0.3, and that's 0.7. They add up to 1. But this 0.3 has nothing to do with that, because that 0.3 addresses the conditional. So that was probably also a good revision last time and today of your knowledge of conditional probabilities. And we're going to look into a so-called graphical model today that often has this kind of structure or a more complex one. And these arrows need to be read in a certain way because they are directed. And obviously, given that there is rain, there is an impact on if the director brings an umbrella or not. So this is how to read this, that the rain influences if there is an umbrella. there's more, or this is written in detail in here, but it's just what I have said, that this is how to read that dependence. Obviously, later when we do inference, we want to know if there is rain, given that the director brings an umbrella, because that's the goal of filtering. We want to infer what we don't know, given the evidence. And then the arrow would be in the opposite direction when you do inference. Today, we'll continue temporal models. We will discuss filtering in greater detail, and then we look at a few more other tasks that temporal models can do. Once we have that, we will look into a very specific filter, which is the Kalman filter, and we'll develop it step by step. And once we have discussed all the theory, I will also show you or explain you how you can actually use this. In real, you don't need to code it from scratch. You can just be using a library. But in order for us to know how the Kalman filter works and what it's useful for, it's good to discuss its theory. And in order to understand the Kalman filter, we simply need to build all this groundwork before on temporal models. Otherwise, we will not be able to understand what the goal of the Kalman filter actually is. There are a few more definitions now. The so-called prior probability distribution at time zero. So time zero, x0, and it's a distribution. That's why we have a bold P. And this is how everything gets started. How to initialize the priors, I don't know, depends on our use case. Maybe in a simple use case for rain, we would say, well, we don't know anything about the initial state. We could just say it's 50-50, or we make some other prior assumption. And then if we look again at this temporal model, we see the umbrella depends on rain, which is the sensor model. And we also have this transition model from rain in time t to rain in t+1. So t+1 depends on t, which is the transition model, and we have the sensor model. And we can describe all of this through the complete join distribution over all the states. So based on that graphical model, what we have is we want to have the join distribution of the states from 0 to t. It starts with 0 because we have the prior distribution, and the evidence comes in as of time click 1. That's something I noted last time. And what is actually the complete join distribution over all the variables given that graphical model? Well, we start with P of x0, which would be in this model just here to the left. It would start somewhere, and then it would transition from 0 into 1, from 1 into 2, and so forth. Plus, we have this sensor model, and we can describe this with this multiplication starting, or I starting from 1 up to t, and we say, well, our state x depends on the previous state. In our example graph that we saw, it's for rain, but remember, these are vectors. They can be far more than just one variable in it. It could be multiple entries, and this has nothing to do with rain. The rain example would be just a specific example. This one here is the more general description of this kind of graphical model. So we see xi depends on xi minus 1. So, for example, x3 depends on x2, x2 depends on x1, and x1 depends on x0, and you have to factor in or multiply p of x0. So this is where it starts, but this product not only covers the transition model, but also the sensor model, because we have the evidence. This would be, for example, the umbrella depends on the rain. And here again, it's more generic because it's a probability of the evidence given the state. So this general definition here of the complete join distribution refers to that kind of graphical model we have just seen. And assuming we keep the graphical model like this, we will now look into filtering and a couple of other tasks. And and describe how we can actually do inference. There are different inference tasks we can do. Filtering. Filtering is the first one we will start with. So filtering is about inferring our state given the evidence and the past states. There are other tasks like prediction, smoothing, the most likely explanation, and learning. And I'll tell you what these tasks are about later. The focus of today's lecture is really filtering. We will now look at very general filtering equations. We'll do this a little bit for prediction, and for smoothing, most likely explanation, and learning. We'll discuss this even less. And once we have done these 5 general tasks, we'll look into filtering in the context of the Kalman filter. When I studied machine learning in my master's, so I did a whole master's in machine learning at Imperial College when I was younger, and there was a whole lecture just covering all of this for the whole semester. That class was called Advanced Machine Learning, and essentially it only addressed inference in temporal models plus learning. So it was a very tough course, and what I'm trying is to compress the essence and probably the most useful part for this course, the Kalman filter, into today's lecture. And last week we already started a little bit, but I remember that class, which I took, advanced machine learning or advanced statistical machine learning, whatever the course was called, was extremely tough in order to understand all of these tasks in detail for various models, not just the Kalman filter, but also hidden Markov model and other things. So we talked about filtering today already, and last time a little bit, and we said filtering is actually, we want to compute the so-called belief state. So we don't know our exact state. However, we can try to infer it from past states and all the evidence. So we can say the belief state is actually a posterior distribution over the most recent state, given all the evidence to date. And filtering is sometimes also called state estimation, which is just a synonym for filtering. And filtering is actually a term that goes back to the early days in signal processing, where the problem was always to filter out the noise in a signal by estimating its underlying properties. And that's why filtering out the noise, that's why we talk about filtering. You can also, however, just talk about state estimation, because we want to compute the belief state or estimate the belief state. And concretely, in our example, we want to compute what's the distribution of x at time t, given all the evidence from 1 to t. And we'll now develop a couple of very general filtering equations. We'll try them out a little bit, and then we see what kind of assumptions the Markov filter makes. And that's most of today's lecture, which will be quite tough. But this course is also meant to challenge you and to get a better understanding of statistical methods. In our umbrella example, filtering would mean we want to compute a probability of rain today, given all these observations of the umbrella, whether the umbrella was carried or not so far. And that's this past graphical model we looked at. And later we see that the other tasks here, like predictions, smoothing, they address something different in that graphical model. And concretely, we want to build a useful filtering algorithm. It needs to maintain our current state estimate and update it because we have more evidence coming in. And we don't really want to go back over the entire history of evidence we have received. So we process the evidence, we continue. We don't always just want to look back into all the past evidence. Otherwise, as time goes by, this would take longer and longer. If for each new evidence I look at and update my state, I would look into all the past evidence as well. That's what I don't want. I always want to look at the new evidence plus my state variables so far, and I want to go back the whole history for each inference or for each filtering, because then it would just take longer and longer the more data comes in. So we can try to simplify this a little bit and say, well, what's the probability now, or the distribution of xt plus 1, so at time step t plus 1, given all the evidence from 1 to t plus 1. What I actually want is, I want that past this posterior distribution xt given the evidence up to t, plus I have the new evidence coming in, and I want some function to calculate this for me without going back into all the past evidence. And what I'm doing here is something that I call a recursive estimation, and how I implement this function exactly depends on various conditions I'm making, or various assumptions I'm making. But we can always calculate, or for now, we view this calculation of 2 steps. So our 2 steps that we're doing is, we want to look at the current state distribution and project it forward from t to t plus 1. And then we want to update it using that new evidence. So we project forward given our transition model, and then we plug in the evidence through the sensor model, which are the 2 key components we revised today and discussed in last week's lecture. Then we will need now something that is called Bayes rule. Who of you still feels confident with Bayes rule? Maybe send me a thumbs up or green sticker. You still feel fine with Bayes rule. If you don't feel comfortable with Bayes rule, maybe a red sticker or a thumbs down. And don't feel shy to send a thumbs down, because we also have exchange students and students from other programs who are, I think we have some students from computer vision, from cybersecurity, for example, who may be new to a lot of the AI problems discussed here. And that's why we will start with a quick revision of Bayes rule. Refers to a Reverend Bayes, who was a pioneer in statistics. And we'll now look into a conditional probability that I want to compute. It's P of X given Z. So X could be a class or something else. We will later use this in our temporal models, but the Bayes rule is far more generic. You can use this for spam filtering. You can use this to recognize language. You can use this for classifying images. So it's a very generic statistical tool. And it turns out we can calculate P of X given Z from the conditional probability of Z given X times the prior of P of X, and we still need to normalize by the probability of Z. Since this is a revision, so you have most students who are taking this course, or all who are taking this as a mandatory course in their AI degree program, they have learned this in their statistics lecture, but we can say that we'll also give them some names now, just that we are all on the same page. So P of X is the prior distribution of X. P of X given Z is called the posterior. And P of Z given X is often called the likelihood. And P of Z is something that I typically call the normalizer. It's independent of X, but it only makes sure that we finally deal with proper probabilities. Sometimes P of Z has some other names. Some people call it the marginal likelihood, but we'll call it here simply the normalizer. And we will now look at an example. This example is in the slides, and then we'll calculate it manually. I want you to be able to read it as well. We will now, just in order to understand how Bayes rules works, we'll be looking at disease testing. And we have a test in order to detect whether someone is sick or not. Like, could be cancer or some other disease. which will turn out actually to be more difficult than you think. So what we know is that D returns a correct positive of 98% of the time and a correct negative of 97% of the time. And now you get a positive test, and the question is, do you really have the disease D? A lot of people think, yes, if the test is positive, they're for sure sick, but it isn't that easy because we don't have correct positives of 100% or correct negatives of 100%. So even if your test is negative, you still may be sick. And if your test is positive, you may not necessarily be sick. And this has not only to do with this correct positive and the correct negative, it also deals with the prior, that only 0.8% of people have a specific or have this specific disease D. And now you get a positive test, and the question is, are you sick or not? And we'll try to calculate this now with Bayes' rule and determine what's simply the probability of being sick given the test. We'll have an example now. So our example was something like, we said 0.8% of people have this disease. So it's a rare disease. So you can say, well, the probability of the disease, independently of any testing, whatever, is 0.8%. So it's 0.008. So we said this was 0.8%. Then we said we have a correct positive of 98%. Correct positive means I have a positive result given I have the disease. So D stands for the disease and plus for a positive test. And this is 0.98. So it's 89% correct positive. And we've also seen that we have a correct negative of 97%. And correct negative would mean negative test given that I don't have the disease. So here I have an inversion from the logic. So P of negative given not having the disease is 0.97. And what I want to know now is, what is the probability of P of having the disease given a positive test? Because this is the one we're wondering about. I got a positive test, am I sick or not? And for this, we can use our Bayes rule from before. So here we have general variables X and Z. And now we can just plug in D or plus whatever. And so we know that the probability of a disease given the disease given the positive test can be, which we don't know from our data, we can reformulate this. Given Bayes' rule, P of positive given the disease times P of D divided by the probability of a positive test. And there are some of these things we have already at hand. We know the prior, so this one is something we've got, and P of plus given the disease is something we have as well. So these are two probabilities we have already. This one down here, P of plus, we don't have yet. So we need to rethink how we can calculate that. And we're now coming to the next step. So this will be a little bit longer. And the numerator of the fraction is fine. We have this already. So P of plus given the disease times the probability of the disease. The prior is something we have already. And the screen part is a little bit more tricky. We can recompute this by saying P of plus is actually P of plus and the disease, so the joint probability, plus P of plus given of not having the disease. So these are two joint probabilities that we add together. And in order to compute this, we're using something that is called the law of total probability, because a test is either you have either a disease or not the disease. These are the two values D can have, D or not the disease. And if you have these two joint probabilities of a positive test and a disease, plus the probability of positive and not having the disease, this is actually the probability of having a positive test. But we also see that we don't have these two new variables we have just introduced. So we also need to write that out. So we could start and say, well, we want to calculate P of plus. So we could say it's P of plus given the disease plus the other one, which is P of plus not having the disease. But we don't know how to calculate them, but we can calculate this actually by taking advantage of another probability rule that you can break up this joint probability by using a condition and a prior. So this is another fundamental rule in statistics. You can say, rather than calculating P of plus and the disease, we can say it's P of plus given the disease times P of D. So this is a fundamental rule that you can do with conditional probabilities. And we need to do something else over here where we say the probability of having a positive test and not having the disease. Well, I'm just using the green one. We again use a conditional probability and here say this is the probability of not having the disease. So we have these two products now, and then we are almost done. We can try to plug this in now from above and try to calculate it. So we still have this one available, the probability of a positive test given the disease, which is here 0.98. And the prior probability of having the disease was 0.008. We also have this one available. So we're building now this step by step. We have our plus here. And this one is also available. It's just as we have in the numerator. So P of plus given the disease, it's also 0.98 times 0.008. This one here becomes more tricky. We need two parts. We need one part, which is a positive test given not a disease and P of not having the disease. So I can either have the disease or not have it. This needs to add up to 1. So having the disease is 0.8%. So 0.008. That means having the disease is very low. So not having the disease is just the inverse. So it adds up to 1. So not having the disease is actually 99.2%. So not having the disease is 0.992, because you either have the disease or not. And one that is a little bit more tricky is the probability of a positive test having or given that you don't have the disease. And what we have here is this probability. We see it's the probability of a negative test given not having the disease. So the probability of a positive test given not having the disease is 0.03, because these two need to add up to 1, because our test can either be negative or positive. So we need to plug in the 0.03, and we need to calculate this. And if you use a calculator, and the numbers hopefully look all correct, this is 0.2085. That means the probability of having the disease is only 20.85%. So we have a positive test. Why is it actually that low? Because a lot of people think I have a positive test, I'm actually sick. It's not that easy, because we have these conditional probabilities, correct positive, correct negative. But another reason is this very low prior, that many people don't have this disease. So a positive test can only be an indication, but it doesn't mean I necessarily have the disease. If this prior goes up, and if the correct positive goes up and so forth, obviously this result would also go up. But so far, with these values, it's only 20.85%. If you go to a doctor and you have more symptoms, for example, you're bleeding or you're feeling really bad, obviously that extra evidence can be plugged in this model by extending it, and then the probability goes up. So if you have symptoms on top of a positive test, obviously the probability goes up, and it goes up quite a lot. But if you have no extra evidence, then this probability stays low. However, if many people have the disease, probably the prior is bigger, and this result also goes up. Have you ever seen an example of Bayes' rule for something like this? Maybe thumbs up, thumbs down. If this is something you have come across before. In this example, you'll find in the literature, in books, in some of my past courses, long before COVID. So this is nothing new. And so this didn't come into the slides because of COVID. It's simply a standard example of how to use Bayes' rule. And this is something you will find in my slides as well. And feel free to do these calculations on your own, or vary those probabilities. And now we needed this Bayes rule because, or needed to revise it, because we're going to use it now throughout this course. So we are using our two-part filtering process from before, because we said we want to update the current state distribution, project it forward, and then plug in the new evidence. And we're going to see now what this looks like in this very general filtering equation, because what we want to compute is the probability of xt plus 1, so our new state distribution given all the evidence, including the new evidence, because it's e from 1 to t plus 1. We can try to break this up and say, well, it's all the past evidence from 1 to t and the new evidence. So we're dividing up the evidence. And now we're actually applying Bayes' rule to this. And you can try this out on your own, but you will come to something like this. It's a little bit more complex because the evidence is broken up. But with Bayes' rule, we're now getting to something like this. Is P of the probability of the new evidence given the new state and the old evidence times the probability distribution of the new state given all the old evidence. So this is something looks a bit more complex, but you can derive this with Bayes' rule. But if you look at Bayes' rule, we always talked also about this normalizer. And in our example, we saw how we can calculate a normalizer. And this is often something that's a little bit more tricky when you deal with Bayes' rule, how you can actually calculate a normalizer, but there are good ways to do it. But often this would just take a lot of space when you write it down. And we don't really need a normalizer. The normalizer only makes sure we get proper probabilities so that these probabilities in the distribution finally add up to 1. But if we don't care about normalized probabilities, we can just leave this normalizer away, and later we will normalize it. So this is something you often see in the literature, that the normalizer is not specifically written out, but it is unnormalized probabilities. Sometimes such probabilities are called evidence, but I don't like the term evidence in the core or in this chapter here, because we use evidence as a term for what our sensors give us. And now if I call this unnormalized probabilities evidence as well, it's something different. And I don't like to use the term evidence for two different things in the same slides, because this would totally confuse you. So what is often done when we refer to these unnormalized probabilities, we put an alpha in front, which is just a normalizing constant. So we don't need to we don't need to write out the normalizer, at least not for now. And then this still looks a little bit tricky, but actually it can be simplified because we make this Markov assumption on the sensor, because we can say, well, or from our graphical model, we know that the evidence only depends on the state, not all the past evidence. This is the Markov assumption we made in this before in the graphical model. So we can just kick this out. We're using the sensor Markov assumption. So all we have now is the conditional probability of the new evidence given the new state times the distribution of the new state given the past evidence. So we always use alpha for normalizing constants throughout this term, and our P of x t1 given all the past evidence actually represents a one-step prediction of the next state, and the first term updates this with the new evidence. And this one is directly obtainable from the sensor model, because we've looked at the sensor model and we saw the evidence depends on the state, something we had also seen in a graphical model. Now, this can be further expanded because we can obtain now the one-step prediction for the next state by conditioning on the current state. These general equations, they look extremely complex, but actually what I'm just doing is I'm computing this one here, this last term, and what I'm doing is I'm effectively just simplifying it, and I find a way to efficiently compute it, which looks something like this. What we're doing, in fact, is I'm saying, well, my new xt depends on the past xt and the past evidence, and I have to add another conditional, and I say xt depends on all the past evidence. This is derived in detail in this Russell and Norvig book, if you care. But later, when we look at an example, we see it actually looks far simpler in an example than here in this highly generic equation. But we can still apply the Markov assumption, because here we say that xt plus 1 depends on the concrete state xt, as well as, because this is the concrete state, but it's a distribution, so I put x into capital and p into bold, and given all the concrete evidence, so the concrete evidence also uses a lowercase e, but the new state only depends on the old state, not the old evidence, and that's where I'm also using the Markov assumption we had put in this graphical model. Later, in a few slides, we will see an example of how this can be computed precisely. There's also some more detail in the literature about that we are actually that we can interpret filtering this new estimate xt given all the concrete evidence that we can think of this filtered estimate as a message f from 1 to t, f from 1 to t that is propagated forward along the sequence, but that's again highly generic, and will very quickly move to a concrete example that this becomes more clear. If you're curious about deriving these equations, this is explained in greater detail in the Russell-Norvig book, but in this course, we are not deriving those equations because it would take fairly long. We'll now look at our example, and what you need to bear in mind is this table here, which again shows our graphical model. We see our new state depends on the past state, and the sensor model is this one here, where the umbrella, or whether we see an umbrella, depends on rain, with the same transition tables as before. And what I want to compute is, what's the distribution of R2, so rain or no rain, given that we have seen the umbrella both in time clicks 1 and 2. So we have seen the umbrella twice, and in time slice 2, I want to know what's the probability of having rain. And I will again calculate this with you. What you should bear in mind are these two these transition tables for P of U given rain and P of rain at T given if there was rain before. So we want to know, I'm putting this as a capital P because it's the distribution of R2 given I have evidence that there was rain, there was an umbrella from 1 to 2. And I want to compute this. So I need to start, and what I'm showing you now is also something you see in the slides where it's well formatted. What I need to start with is P of R0. And I say, well, this is a vector 0.5 and 0.5, because it either rains or it doesn't rain. I don't know, because I don't have any evidence yet. I just have this initial prior. So I say it's 0.5, 0.5. If you look in the slides, just in order to save some space, I often write this out not as a column vector, but as a row vector. So I write 0.5 and 0.5 as a transpose, which is just a row vector. Here now, since we have more space on the iPad, we can use these column vectors, but in the slides, I often use these row vectors, just that more steps fit on each slide. That's exactly the same. It's just a row vector that I transpose, which gives me a column vector. So this was the first one. And now I want to know what's the probability of having rain at R1. I can calculate this with these past equations. I say, well, I'm going through whether there was rain or not in R0, and I have my distribution of whether it rains in R1 given what I knew before in R0 times P of R0. So this falls off as a special case from these very generic equations we have seen before. And the way I can calculate this is, well, I have my P of R0 up here. And here I need to take into account these transition probabilities, these two tables. And we knew if there was rain before, the probability of having rain in the next day is 0.7%. And it's 0.3 the other case. That's what you saw. So we'll now calculate this in a vectorized way. So this is the 0.7, which means we have rain now, given we had rain yesterday. There's a second entry, which is just the other way around, 0.3 times P of R0, and we're starting, since this is a sum, we're starting with this 0.5. This is the first iteration of the sum. But for R0, we have two values, this 0.5 and this 0.5. We have the other 0.5. And here, this is just for the negative case. And if you look at that transition probability for the negative case, that means if there was no rain the day before, the probability of having rain today is 0.3 because there was no rain before. Now the probability of having rain today is 0.3. And since this needs to add up to 1 with the next entry, it's 0.7. If you calculate this, you see we have actually not learned anything, because if you calculate this, we see it's still 0.5 and 0.5. We don't know anything in our transition model, or we haven't learned anything, because all we saw is we just did a transition from one day into the next day. But now we will actually, in the next step, take into account our evidence. And the evidence will come very quickly now, because we know that from what I wrote here, we know there's an umbrella on the first day and the second day. So I can now calculate P of R1 given the evidence. And from our graphical model and from these filtering equations, we saw, well, we can use Bayes' rule here. So P of U1 given R1, since I'm applying Bayes' rule, I also need this prior of R1. I don't want a normalizer, so I'm just putting an alpha there. And we'll continue. That's our alpha. And this one here of having an umbrella given there was rain, we saw that this is a probability of 0.9. This is the second transition table in our graphical model that we had looked at. And what we also saw is that here we get a 0.2 because this was just the other entry in the transition model, where we said if there was no rain, then the probability is 0.2 of having an umbrella. And now we need to do this sign here. It's written like this in the slides. It's an element-wise multiplication. And P of R1 is just this one. So it's 0.5 and 0.5. Element-wise multiplication means we multiply these two, and we still have our normalizing constant. So 0.5 plus 0.9 is 0.45, and the other one is 0.1. We want these to be concrete probabilities, but they are unnormalized. So the way we can normalize them is we are dividing 0.45 by the sum of 0.5 and 0.1. And 0.1 is divided by the sum of those two as well. And this is how you actually normalize. And we didn't have to worry about the normalization before, because now normalizing is fairly easy. So we always just put our alpha before, and this will give us some vector of something that is 0.818 and 0.182. So all we have done now is the umbrella came in once. And there's a question here of how this is applicable to computer vision. I said the Kalman filter is applicable to computer vision, but in order for us to understand the Kalman filter, we first need to understand the temporal models. So we're just doing now probably some of the simplest tasks we can do in filtering. Once we have understood this, we can build a Kalman filter, and that one can be used for image sequences. So it takes us a little bit to make it there. But once we have discussed this from this general perspective, you can use the Kalman filter for all these other problems, not just in images, but many more signal processing problems. But it takes us a bit to get to the Kalman filter, because if we don't discuss temporal models in depth before, you will be totally unable to understand the Kalman filter. And if you just use a library that includes the Kalman filter, probably you don't know how to use it, because you need to have an understanding of how this works. Now, we have done this for one evidence that came in, but we said we need another evidence, which is in the second time step. So essentially, we are just repeating what we have done before. All I need is to redo more or less what we had done. It's a slightly more complex because it's one time step away, but I'll show you this now simply in the slides. And then we're already done with this filtering example. So this is what we just did. And now on day 2, the umbrella appears again. What I need to do first is calculate R2 given my past evidence. So this is just one time click that I look into the distribution of P of R2. And it's more or less just what we did before when we wanted to calculate R1. The only thing is now we still have this evidence from before. And this was this evidence, and the other one, or sorry, this was the probability of having rain in R1, and this was the evidence of not having rain. Those are the ones we have just calculated, and these transition tables are the same from before. So we're just calculating more or less the same equation as before with new values, and then we see, well, we are now going into time click 2 and say the probability of R2 given the past evidence. And these probabilities are actually getting a little bit uncertain than before, because we have our transition model, but we don't have new evidence. We're just using the evidence from the time step before. So before we did this transition, we said, well, the probability of having rain is 0.8%. Now it's only 0.6% because we're now less certain. But we can now update this in the next step with the new evidence. And our evidence, U2, is simply that we saw again an umbrella in the second time click. But because of the Markov assumption, R2 given U1 and U2 becomes simpler because we plug in the new evidence. The old evidence is still in the model. And we're just doing the same calculations as before. And we will see, and we're doing this dot-wise multiplication, we see now we have an 88.3% probability of having rain because we saw the umbrella twice in a row. And if you do keep doing this 10 times, this probability will go very close to 1. And this one will go very close to 0 because it's super likely that it's simply raining all the time if an umbrella comes in all the time. If you want to try this out on your own, maybe in the next step, you could say there is no umbrella coming in, then the probability of having rain right now is probably far less. But that's something you can try out on your own. We have now seen the filtering task, and in the Kalman filter, we will make a few more assumptions how we can calculate this. Briefly, I also want to introduce these other tasks to you in temporal models that we're not using in the Kalman filter, but they are there. One is prediction. Prediction has a different goal than filtering. And in prediction, we actually want to compute the posterior distribution over the future state, given all the evidence to date. So we are introducing a variable k, which is greater than 0. So how many steps we want to look into the future. And what we are looking at is x of t plus k, where k is greater than 0, given all the evidence up to t. And prediction is useful for sort of looking into the future or evaluating possible courses of actions based on our outcomes we have so far. In our umbrella example, this would mean concretely that we want to compute the probability of rain 3 days from now, given all the observations we have up to date. So we're not looking into future evidence, rather the evidence we have right up to now, and we want to look into the future without additional evidence. This can be described with these, again, with very generic equations, which is derived again in the book. But what is key to here is that this part is key, that we say we have the probability of xt plus k plus 1, so k something greater than 0. And we go through this at xt plus k, and we are only including here this transition model, not the sensor model, because a sensor model would mean I have more evidence, which I don't. There are 2 more tasks I quickly want to share with you without looking at these equations, but just that you know about the terminology. One term is smoothing. Smoothing is the task of computing the posterior distribution over a past state, given all the evidence up to the present. What is that useful for? In our umbrella example, we could compute the probability that it rained a few days ago, for example, last Wednesday, given all the observations we have up to today. And with smoothing, we can in fact get a better estimate of a past state than it was available at the time, because we have got more evidence in the meantime. And smoothing is helpful. For example, smoothing is used when tracking objects with an inaccurate position, because then we got more evidence over time. And then looking again at these past states, we could estimate a much better trajectory than filtering. So smoothing addresses a different use case than filtering. We also had prediction, and concretely smoothing, we could write out that I want to calculate the distribution over xk, where k is somewhere between 0 and t, so somewhere in the past, given all the evidence up to t. There are, similar to filtering and predicting, there are very general equations for smoothing, as well as the next task, which we call the most likely explanation. But this is something we're not discussing here. If you're curious about what these general equations look like for smoothing and explanation, or most likely explanation, look into the book. There's one more that we call the most likely explanation. And with the most likely explanation, we're trying to compute something different. For example, if we look at our umbrella example, imagine that the umbrella appears on each of the first 3 days and it's absent on the 4th day. We're just we are just recording the evidence, and then the most likely explanation, we actually could argue that it probably most likely rained on the first 3 days, and then it did not rain on the 4th day, because 3 days in a row the umbrella came in and then not. And what the most likely explanation actually tries to compute is, we have our probability distribution of x1 to t given all that evidence up to there, and I want to argmax this. So argmax means I want to find the input, the x's from 1 to t, that would maximize this conditional probability. So argmax means which input maximizes this. So I don't care about the maximum value here, rather which input maximizes this. And such algorithms are very useful, for example, in speech recognition, where the aim is to find the most likely sequence of words given a series of sounds. And we want to have, in the series of sounds is eventually a reconstruction of bit strings transmitted over a noisy channel. And one algorithm that is very well known for the most likely explanation is called the Viterbi algorithm, which I've just sent here in the chat. In addition to those 4 tasks, there's one more task which we call learning, because in some settings you may actually not know the transition and sensor models. We have always assumed now that we have the transition and the sensor models. In our umbrella and rain example, these were these conditional distributions for which we have these 2 tables. Those are the transition and sensor models. But in some settings, you may not know them, and you can also learn them from observations. This can be done typically with the EM algorithm. And the EM algorithm is something we saw and applied it to clustering a few weeks ago. But I said that EM is something far more generic, and you could use the EM algorithm for the transition and sensor model in order to learn it if you don't know it. When I studied my machine learning masters, we spent a couple of weeks just on the EM algorithm, which was a very tough experience, but something we're not doing here because we'll be focused on filtering. Now, we have done these examples with probabilities of if there was an umbrella or not. This can be easily linked to vision because, for example, our human sees whether there's an umbrella or not. So in your vision system, this is where you could plug, for example, a neural network that recognizes if there's an umbrella or not, and that tracking in the background of the state is done by our temporal model. And I've seen quite a few student projects in the last few years in this computer vision course. They used Kalman filter, something special filter we'll look at now, for example, in order to track certain objects. So they had a video stream, for example, in playing pool or cars or whatever, and they wanted to track objects with a camera. And for that, the Kalman filter was used. So we've put in these probabilities into our filtering model, but somewhere they need to come from, or that evidence, and that evidence is not necessarily just, you know, a number that we've made up here, but it could come from a vision system that detects something. And that's the evidence you would then put into the filter. And this is exactly the link to computer vision. And the advantage of these temporal models, they are highly generic. You can put in vision data, you can put in something totally different, and they're highly generic simply. And all these 3 examples we motivated in end of the last lecture was the bird's flight, the radar, and the planets, or estimating where those planets are from observations. All those 3 have one thing in common: we are doing filtering. And what we are doing is actually we estimate the state variables, for example, the position and the velocity. But what is very important is noisy observations. And that's why we have worked with these transition tables. because those allow us to handle noisy observations over time. And what these three models or these three examples have in common is all our variables are continuous, because the position and the velocity of the bird's flight, the radar, and the planets, they're continuous. They're not discrete variables. The examples we have seen with the temporal model and the example filtering, whether there is an umbrella or not, there was uncertainty, yes, but the variables are discrete. There's either an umbrella or not. And that's why we had this one probability and the other, and they added up to one. But now, our three examples of the bird's flight, the radar, and the planets, our variables are continuous. And continuous makes this different. And this is what the Kalman filter will address. The Kalman filter will address, we have noisy observations, we estimate a state, and that estimation is also uncertain, and the variables are continuous. If the variables were discrete, we would use a slightly different temporal model, which we call the hidden Markov model. A hidden Markov model allows us to handle or allows us to do state estimation from noisy observations, but the variables are discrete. And the hidden Markov model, or in short, HMM, is a very popular statistical model. Was very popular in the machine learning domain for many years, used, for example, in speech recognition quite a lot. Nowadays, the hidden Markov model has become less popular in machine learning, because for speech recognition tasks, deep neural networks have become more practical. But the hidden Markov model still has its application for other problems in statistics and machine learning. But for speech recognition, probably neural networks are now far more common. The Kalman filter, however, you can replace it in certain tasks with a recurrent neural network if you wish. But the Kalman filter, again, is a highly generic model, and you can use it for lots of problems. And neural networks are not in general better than all these other models, because for neural networks, you need to do very expensive training. You need a lot of training data in order for them to work well if they're deep. And you not always have that at hand. You may not have enough data available, or not enough training resources. And that's why don't always rely on neural networks. There are recurrent neural networks, and it's something you learn in your deep learning course. But today we are completing the Kalman filter, which is a very helpful model for a lot of different signal processing problems. And quite some students have used it over the last few years in the projects of this course. Mentioning projects, next week I'll say more about the projects. You have probably seen my message in iLearn that on a date in May, you need to present your project proposal, but I'll say more about all of this next week once we have actually progressed with the content. But meanwhile, you already can think maybe about a certain computer vision problem that you are interested, that you want to investigate in your project in a group, but more about how to find a group or how the marking goes and what my expectations are, something I'll discuss next week. So the Kalman filter, again, allows us to handle a series of measurements. We want to estimate a state. These measurements have noise, so they're noisy, and other inaccuracies. And our state is also an estimate, and we're dealing with continuous variables. We can look at our bird's flight from before. In the bird's flight, we actually have 6 continuous variables at each time point. Because what we want is we want to estimate where our bird is, but the measurements, so we see the bird, is uncertain, because sometimes the bird is just hidden behind a tree, and we want to estimate where that bird could be right now. We have 6 continuous variables. 3 of them are the positions in X, Y, and Z, the 3 dimensions, plus we have those 3 velocities. And In this section, in order to describe velocities, we say xt and put a dot on top. That's a notation you often see in physics in order to describe the derivative or the change of the variable, and the change of a position is its velocity. So xt and the dot on top is the velocity along the x dimension. We have the velocity along the y dimension and the velocity along the z dimension. We need conditional densities to represent our transition and sensor model. So they will be more complex because we need to be able to handle noise. And what we are using are so-called linear Gaussian distributions. This is all based on Gaussian distributions that we see soon, and the linear Gaussian distributions, they make a few extensions to this. We're not explaining linear Gaussian distributions in detail, rather the few points where I need them. I just highlight why this is a linear Gaussian distribution. And what it means concretely is that our state xt plus 1 must be a linear function of the current state xt. It's a linear function, and we add some Gaussian noise. And a Gaussian noise is typically a condition that turns out to work quite reasonable in practice. There are other Kalman filters with nonlinear extensions and all of this. This is something we will see at the end of the chapter. But for now, just bear with me that these linear Gaussian distributions are a reasonable assumption we're making. In order for us to be able to use these linear Gaussian distributions, we should briefly revise the Gaussian distribution. Who of you feels comfortable with the Gaussian distribution? Just regular Gaussian distributions in one dimensions, maybe thumbs up or thumbs down. So thumbs up means you feel you're a pro in understanding what the Gaussian distribution is about. Thumbs down maybe means you wish to have a quick revision or something, or that you don't feel that comfortable with that distribution. It's definitely something that was covered in your statistics course, but we'll do a quick revision because then we will extend it to many dimensions. So probably one of the most important probability distributions ever is the Gaussian distribution, which we also call a normal distribution. And the Gaussian distribution has two parameters. One is the mean, mu, and the standard deviation, sigma. And in fact, if we square the standard deviation, we have the variance, which is called sigma squared. And the density can be described as following. We say P of x is 1 divided by sigma times the square root of 2 pi. And then it's e to the power of minus x minus mu squared divided by 2 times the variance. The interesting part is this exponential, but we say that x, our input, is a continuous variable ranging from minus infinity to plus infinity. And if we integrate this density from minus infinity to plus infinity, we want the area to be 1, because that's what we expect for a probability distribution. And so that when we integrate this from minus infinite to plus infinite, we want the area to be 1, or the integral to be 1. So the area between the curve and the x-axis. And in order for this to be 1, we did a normalizer. And the normalizer is we divide this by 2 times pi, the square root of that, times sigma. Sometimes you see that the sigma is just put in here, that it's 2 times pi sigma squared, and then you take the square root just the same. And so you have a sigma squared in the square root, or you move the sigma out of the square root. Sometimes the Gaussian distribution is referred to as n for normal distribution with the two parameters mu and sigma squared. There is a special case where we say the mean of the distribution is 0 and the variance, so sigma squared, is 1. And if that's the case, we actually talk about a standard normal distribution, and you can plot it. You can customize this for you with the mu and sigma squared. So the normal one is the red one. It's this red curve. We see its mean is 0, and then it goes like this. The blue one is thinner because sigma squared is 2. And if sigma squared is greater than 1, for example, 5, so the orange one, it more stretches out. And what we can also see is we can move the mean to -2 with sigma squared 0.5. And if we integrate each of those for functions from -infinite to +infinite, it will be, the integral will be 1 in each case. So they all have the same area under them because we have this normalizer in front, which depends on sigma or sigma squared. The normalizer does not depend on the mean because the mean is just a shift on the x-axis. So this is something you have probably seen in your statistics course, and the Gaussian distribution is used for lots of applications in machine learning. For example, in a lot of machine learning models, we assume that the errors are normal distributed, and you see plenty of other applications where this is used. So if you're in one of those AI programs, you have to feel comfortable. There were a few students who wanted a revision. I assume they are from one of the other programs taking this course as an elective. Now, we have one dimension x. Who of you has seen the normal distribution in multiple dimensions? If you have seen this in multiple dimensions, maybe thumbs up. If you have not seen this, maybe thumbs down. Probably not a lot of people who would so far have thought about this in multiple dimensions, which you also need in practice when you deal with multiple variables at the same time. And the Gaussian distribution can be described in multiple dimensions. Now x is in bold, which means x is a vector because it has multiple entries, n many, so we have an n-dimensional vector. And for such a vector, the Gaussian distribution looks something like this. Looks far more complex than the one before, because here we set x minus mu squared divided by 2 times sigma squared, plus we have this normalizer. But it turns out, I have to admit, I don't know this by heart. So if you just approach me in a corridor and ask me if I can write you out a multivariate Gaussian distribution, probably I would need to think about it again. Or I would need to prepare just in order to be fully able to revise it on the spot. But it doesn't look that different. What is the same is we have an exponential, there is something in the exponential, and we have a normalizer. And there's still a 2 pi and a square root, but there are some more elements. Remember, if you look at this, before in our Gaussian distribution, x was some real value, in mu the mean as well. Now x and mu are bold. That means x is a vector, n entries, and mu is also a vector because now we have n dimensions, so we also need a mean in each dimension. That means mu is now a vector containing these means, and x is our vector with n dimensions. And before I did something like x minus mu and I squared this, and this time I'm doing something that isn't that different. What I'm saying is I'm taking x minus mu, this time not scalars, but this time I have these two vectors, and I'm multiplying this with x minus mu. But here, this is now transposed. And in between, I have this large sigma. And before, I used the sigma down here in a normalizer, and this sigma was my variance, and I need something like this as well in a multivariate Gaussian distribution, but I use this sigma, which is the covariance matrix. Covariance is a generalization of the variance because it's how two variables, or the variance of two variables, which is just a normalization. Sorry, no, it's just a generalization. And this covariance matrix describes simply in its entries how two variables, or how it's sort of a correlation, but it's not really a correlation measure, but it's simply how two variables relate to each other. And in the diagonal, you could have, for example, the how one variable relates to itself, which would then be the equivalent of the variance in the single dimension. But I need to take the inverse of that matrix, and eventually this one up here is still multiplied with -1/2. How to derive the multivariate Gaussian distribution is something would be done maybe in a statistics course, but for now we just assume it looks like this. But you don't need to remember this by heart. And again, I need a normalizer, and it turns out a normalizer is something like this. Again, I have a square root. I have my 2π, but I have multiple dimensions. So I need to raise this to the power of n, and I need to multiply this with the determinant of the covariance matrix. Lots of elements, I know this, but what is it useful for? So it's a multivariate Gaussian distribution. We can try to plot it in 2 dimensions. Now we have a 2-dimensional data set. So we have x and y, which are my 2 variables, and I have spread out a data set in here. And we see, well, this is actually normally distributed. This is the first principal component, and then we have a second principal component in this data set. And we see up here the distribution along y, and here the distribution along x. And this looks like a normal distribution. Obviously, they have different, these 2 dimensions have a different variance, and we also need a covariance because we see there is some covariance between x and y. And this is what a multivariate Gaussian distribution would look like. You can imagine that this works for more than 2, or for more than n equals 2, n equals 3, 4, 5, n in the thousands, but it's something that we are unable to visualize here. And we will need this multivariate Gaussian distribution in a Kalman filter, but in the simplest form in our Kalman filter, we're just looking at a single variable. In our example here with the bird's flight, we actually have 6 variables, but just in order to keep it easy for now, we will just work with a single variable. And again, what's the link to vision? Well, you could have a camera that simply provides us evidence of if we have seen a bird or not, but it's an image sequence that our camera is recording, and sometimes the bird is hidden, and then the camera doesn't give proper evidence. But in our temporal model, we're actually then able to do a state estimation based on the current evidence as well as the past evidence and the past state. So this would be, again, it's highly generic. We can plug in vision data, we can plug in totally different data, and that's the beauty of this approach. The Kalman filter is actually something that was derived for the first mission to the moon, when humans were sent to the moon. This is some, there was lots of fundamental and applied research for the moon missions in the 60s, and the Kalman filter was actually something that was derived in that framework of that research as well. Concretely, the Kalman filter is the exact date or exact year. I'm trying to find it. So the Kalman filter was proposed at least in the earlier works in the late 50s, early 60s, and then massively extended later. But it's certainly something that helped to bring humans to the moon. So that's probably a cool extra information on the Kalman filter. And it's still used today for lots of applications. And some students use it every year for the projects in this course. So we will now just look at the x coordinate. We will not look at the other coordinates. We'll just keep it simple. And we want to ignore the other coordinates, and we make observations every a certain number of time that passes, every second or every 100 milliseconds, whatever. But the time interval between observations is just called delta, and we assume constant velocity during the interval. This is something that we're doing now as a simplification. And if we assume that, so we have a certain time between observations and there's constant velocity during that interval, only during that interval, obviously, not in general, then we can update this position by something, well, our new coordinate x at our time t plus 1 or plus delta, how much time has passed, we say it's xt, the old position, plus the velocity of x, so x dot, time how much time has passed, which is our delta. And I said so this is the linear part, and we're using these linear Gaussian models. There is uncertainty because we just don't know how much it moved exactly, so we need to add Gaussian noise on top of it. And Gaussian noise is particularly helpful because the Gaussian distribution largely, or it's most likely that you're expected, or that what happened in the real world in this case would be close to the mean. And the further you go away from the mean in the Gaussian distribution, the less likely it is. That's exactly what that density means, because there is uncertainty. There could be wind, there could be whatever. And we can then say our probability of xt plus delta, and it's a probability distribution because it's a continuous variable. So this is in capital, and our concrete measurement, or our concrete value xt plus delta, the one we had so far, given xt and the velocity, can be described with a normal distribution where our variance stays, but we say our mean is xt plus the velocity of xt times delta. So this is how much we assume the bird has actually moved. This is the mean of the Gaussian distribution plus our fixed variance. We'll discuss the variance later in greater detail. And we plug in our xt plus delta. And this is how we're describing the normal distribution, and we have now a linear Gaussian transition model. This can also be described with a Bayesian network or a graphical model. We've seen this kind of figures before for our umbrella and rain. Concretely, I call this at that time step a graphical model, which is a very generic term, but graphical models can refer to many kinds of graphical structures that represent linear systems or linear dynamical systems. Concretely, we have a so-called Bayesian network, because there's more than Bayesian networks in the field of graphical models, but this is a Bayesian network. And our Bayesian network, we have all these entries in here. I want to show you, we have our position xt, that's the position, and we have a position measurement, zt, because that's what we have measured or what we have seen, but there is noise in it, so we want to estimate the position xt, that's our goal. Xt plus 1 depends on the past xt plus the velocity of xt. And this is exactly what we have done in the previous equation, because we said xt plus 1 depends on xt and the velocity. And then we have our measurement, which depends on the real world, but we only know the measurement and we want to estimate the real world. This is how you have to read this Bayesian network. If you're curious about Bayesian networks, again, there is a lot of theory about Bayesian networks that helps us to do inference in certain settings. When we care about causality, for example, this can be used. It's a completely different direction in machine learning. Again, when I did my master's in machine learning, I spent one whole course only on Bayesian networks. I tried to compress the key essence in here, what we need for this Kalman filter to describe our linear dynamical system. It's linear because we have made this assumption here that, or here, that we update our x by taking the velocity and how much time has been spent until the measurement or between an interval. And that's the linear assumption. And we add Gaussian and noise, and that's why it's a linear Gaussian transition model. Now, a key property of the linear Gaussian family is that we say it remains closed under the standard Bayesian network operations. That means when we make all these inference tasks, we can always assume this kind of graphical model, which will severely simplify our calculations. And again, we actually have such a two-step filtering calculation. We've discussed this before in these highly generic temporal models. We're just doing now exactly the same specifically to the Kalman filter, where we assume continuous variables, we assume noise, and so forth. And what we need in our model is we have our current distribution, so the distribution of x, and this time this x is not discrete like in those examples about filtering before, but continuous given all the evidence. This is a Gaussian, and the transition model where we say p of xt plus 1 given the past xt is a linear Gaussian. If you assume this, then the one-step predicted distribution can be written out as such, which means the probability of xt plus 1 given all the evidence, because now I'm going to the next xt given all this evidence. And then what I can say is it's an integral. This time it's not a sum anymore, because when we looked in our temporal models, we used sums to describe this because it was discrete. Now it's continuous, so we need integrals. And we say, well, we use the transition model, which is xt plus 1 given xt times p of xt given all the evidence. We have introduced this before, and it's an integral along xt, so dxt. And this is also a Gaussian distribution. So this is essentially just what we discussed before with our temporal models and doing a filtering, but this time this is done for the Kalman filter with continuous variables. So it's an integral. Then the second step in our two-step procedure is the prediction. So we've done now this one here, and now what we want to do is that we want this one here, we want to plug in the new evidence. So p of xt plus 1, given all the evidence and the new evidence, we know that p of xt plus 1, given the evidence, is Gaussian. That's what we said before. And the sensor model is linear Gaussian. And if we use our equations from before and update them for the Kalman filter, we can say that the probability of x t plus 1 given all the evidence, including the new evidence, is the probability of the new evidence given the new state. So this is the sensor model, which is linear Gaussian, times the probability of xt plus 1 given the evidence. And this is Gaussian. This is just a consequence of these general equations we have derived before. And these are unnormalized probabilities because all of this here is a consequence of the Bayes rule, as we saw before. And that's why it's unnormalized, but eventually it's also a Gaussian distribution. This will become a little bit more complex, a few more details, and then we're actually doing this for another example in a single variable, and then we see how you can actually take advantage of the Kalman filter. This forward operator, so we talked before about these forward messages, it takes a Gaussian forward message. What we specify is a mean vector and a covariance matrix, and we're producing a new multivariate Gaussian forward message. And when we do that update, we have a new mean vector, and a new covariance matrix. And the book derives these equations in a little bit greater detail, but what I think in order to keep this also more applied and that you're able to understand it is now we're using, there's a great, excellent demonstration for a one-dimensional example that we will discuss now. So the one-dimensional example, it could be just that one variable like x. And what is shown in the book is there's lots of text in here that I will cover in my oral explanation. Sometimes you find a lot of text in my slides, which is only meant for you to do a revision if you wish. So we said we only have a single variable now, like the position in x, and it's a Kalman filter, so it's uncertain, and these variables are continuous. So we can describe the position of our bird in the prior state, x0, as a Gaussian function, because we have some mean where it starts and some variance. The variance is something when you build your Kalman filter that you need to define. You need to make some assumptions about the variance, and you need to fit it, or you try multiple variances until it works. Depends on your exact setting of how certain or uncertain you are. Don't make it too tight, don't make it too narrow. If you make it too tight and the uncertainty is a bit more, then it will not work. If you make the variance too broad, then the model will probably also not work very well. So the exact variance is something you need to determine experimentally in your concrete setting, but it isn't too difficult. And we see this is the normal distribution, and because we just want to keep the slides as simple as possible, we leave off the normalizing. So we just put an alpha here again in front, and we say this is to be normalized. And you've seen already today how to normalize a Gaussian probability distribution, but we're just putting an alpha in front. And we are always using the same alpha for all normalizing constants. Even we don't enumerate them like alpha 1, alpha 2, whatever. Just an alpha means it's unnormalized and you need to normalize it. And for a Gaussian function, it's a Gaussian probability distribution. It's again fairly easy. You would just divide by the integral, and then you have normalized. So because before we divided by the sum of something in the discrete case, and in the continuous case, you would just divide by the integral. Now we need, the next part is our transition model. And the transition model, what it does is it adds Gaussian noise as well, because the transition model, and this is something we've also observed before in our initial rain and umbrella example, we just transition from one state to the next state, we're actually losing certainty because we have just evolved in time, but we have no extra evidence. And again, we can describe such a transition from one state into the next state. So the transition from xt into xt plus 1, we can again use a Gaussian distribution, because we are writing xt plus 1 minus xt, the mean, divided by the variance in our variable x, and we have this minus 2. We could also just move, or minus 1/2, we could also just move the minus 2 into the denominator of this fraction, as we have seen this before, because in the first definition it was like divided by 2 times this, and now we have moved the 2 out. This is just to keep it a little bit understandable, and later we will make certain transformations of these terms, and that's why it's quite helpful to move this 2 out. So from divided by 2 out to minus 1/2 this thing, but doesn't change the value. It just becomes a little bit easier to understand, and we are separating later these individual components, and that's why it's helpful to move the 2 out from now on. The sensor model also assumes Gaussian noise, because we have our mean xt, and we have the concrete measurement. And here again, for the measurement, we need uncertainty, because what we measure is not fully certain. And then we also need for our measurements a Gaussian noise. It's all, again, unnormalized. Just to make it look simpler, we always put an alpha before. This, again, a Gaussian function. And I also have a variance in my measurements. So I have a variance in the position, and I have a variance in the measurements. Now, what I want to do is, I have my prior, which I always need, because I need to have some prior state where x0 could be. This is something we have done here before. And we have our prior distribution, and now we want to do a one-step update. I want to transition from x0 into x1. I don't have evidence yet. And before, we have done exactly that also for our umbrella and rain example. But this time it's a Kalman filter, so I don't put a sum here and before than what we did. Because before we called this the rain at time 1, given the initial probability of rain times the probability of rain and so forth. And this time it's the positions x, so it's more or less just the same equations than before, but this time it's not discrete, it's continuous. So I cannot put a sum in front, or I cannot put a sum sign in front. Rather, I'm taking the integral where x goes from minus infinite to plus infinite, because it's a continuous variable, but all these elements are the same as before. And before we've defined them and said, well, this is a Gaussian function, this is a Gaussian function, and so forth. And now I'm just plugging them in, those we've just defined before. And you've seen them all here, exactly those that we're plugging in. And we have this exponential and this exponential. And because we want to simplify this later, we are actually just merging these two exponentials, because it's one exponential times the other exponential. So we're just adding these two fractions, and if you add these two fractions, you get something like this. But this is just high school maths, adding two fractions. And we now have this integral. It looks complex, but actually, looking at it, it's just a sum of two expressions that are quadratic in x0, because we have our x0 always squared. And hence, these integrals itself are quadratic in x0. And there are a few more equations, and then we're done with equations in the Kalman filter. But starting initially from the temporal models, it was sums, now it's integrals. It's not just transition tables, but rather we describe those probability distributions with Gaussians, but it isn't that much more complex. And there's a little trick we need to apply now. This one here looks too complex in order to compute it efficiently. So we need to rewrite it. And there is a technique that is called completing the square. Has any of you ever heard about completing the square? If you have thumbs up or thumbs down. So quite some have heard it. That's good. So completing the square isn't that complex, in fact. Completing the square allows us to rewrite any quadratic, which is like a times x0 squared plus bx0 plus c. We can re-express this as the sum of a square term, which is a times x0 minus b divided by 2a squared, plus what we sum on top of the square term is a residual term, which is c minus b squared divided by 4a. And the residual term is independent of x0, and this will severely simplify our integrals. Because if we have this integral from before, and we can rewrite it as completing the square, where we have this term, plus the residual that is independent of x0, we can actually just move this out. How to rewrite this exactly is a little bit tricky, but I almost got only thumbs up for completing the square, so you should be able to do this. But for now, just trust me that the result looks like I have my normalizer times the residual, and the residual is, we're still dealing with these exponentials, but I was just able to rewrite these terms with completing the square. It's something like e to the minus 1/2 times c minus b squared divided by 4a times this integral, and the integral is from minus infinite to plus infinite along x0, times e to the 1 divided by 2 times a times x0 minus, and there is the fraction minus b divided by 2a squared. It turns out that the integral here to the right is just 1 over its full range. This is something you can actually show. And if you do that, you're just left with the residual term. So if this is just 1, can be shown it's just 1, and then it doesn't matter. So we're just left with the residual term. And then we actually notice the residual term is quadratic in x1. And after we apply our completing the square and simplify it a bit, we get to something like this. We see the probability of x1 is our Gaussian function, where we write in here x minus mu0 squared divided by the sum of two fractions that are, two variances that are squared. And the variance is actually our variance 0, the initial variance, and the variance along x. Plus, we have this normalizing constant. And this now is actually fairly easy to compute, because all our x1 depends on now is the mu, so the mean, and the variances. Nothing else. So this one-step predictor distribution is, again, a Gaussian with the same mean y mu0 from before, and we have these two variances. This actually is something we'll generalize a little bit more later, and it's actually one of the key insights of the Kalman filter, that such updates, like in this case, only depend on the mean and the two variances, the original variance and the transition variance. What we have done now is find the distribution of Px1, but we also now have evidence coming in. And if you remember our equations from before, from this general temporal model, it was something like P of Z1 divided given x1 times the prior of x1. We call this the umbrella and the rain, and we had also put a normalizing constant as before. This is exactly what we had done in our temporal model, but because these are now not transition tables, but rather something more complex, and what they are, we have defined before. In fact, they are also just Gaussians, because our distribution over x1 is something we had just calculated in the last slide, and our sensor model can also be described as a Gaussian. That's something we had said already before as well. Now we have this term, which again doesn't look great because we have these two exponentials. Rather, we can have one exponential where we have this one and sum it with this one. So we sum these two fractions. And if you combine these exponents and you do completing the square, you will get to something like this. I'm not reading this out, but this one has, it's a little bit of algebra to make it to here, because you need to sum these, you need to combine these exponents and you need to complete the square. But once this is done, we actually see that our P of x1 given z1, what we need in it is the x1. We have our variances, variance 0, variance x, but also the measurement variance. And we have the mean in mu 0. Plus we have the z1 in our measurement. And like this, if we have rewritten this, remember from the Gaussian distribution, we said x1 minus a mu, and this mu is actually just this. So our mu plus 1 is just this term, and the mu only depends on the measurement, the past mu, and all these variances. And this is the variance we're dividing in the Gaussian, and this variance only depends on all these variants at time t, in x, and in z. As I said, deriving this is a little bit more tricky, but I only put in the result. When you complete the square, you get to there. And this is actually a very convenient feature of the Kalman filter, because using these Gaussian formulas, using completing the square and simplifying all of this a little bit, we see that the new mean and variance can be calculated from the old mean and variance. What we have done here with these equations, they're just playing the same role as the general filtering equation we had derived before. But this time we use our Gaussian distributions and linear Gaussian distributions. And there are some more interesting properties that I'm sparing you for now. Feel free to read this in your revision, but eventually it's just an extended explanation why these two terms are so good. But I've already said this, the mean and the variance just depend on the old mean and variance. And this makes calculating this super easy. And actually these super complex integrals from before, we have largely eliminated, or we have eliminated them just by completing the square and merging these exponentials. Some more text. There is a little example for you to maybe get more out of this. Well, I need the whole slide. What we have is, we have a Gaussian distribution for x0. So it's this distribution in red in here. we see this one, it has a mean, so mu0 is 0, and it has a variance of 1.5, so the variance in x0. We say the transition noise is sigma x, which is 2, and we also have a sensor noise sigma z, which is 1, and we have a first observation of the position at Z1. So we are starting with some estimate of the position. We say around 0, we put our Gaussian distribution here, which is a bit wider than the standard one. It's 1.5. And we have our first observation. But first of all, because we start with P of x0, we transition to P of x1 before we look into the measurement. And we see just transitioning from P of x0 to, or from x0 to x1, actually reduces our certainty. This is something we have noticed throughout all these examples, that if you're going from x0 to x1 or from x50 to x51, you're losing certainty. And that's exactly what we can see here, because this Gaussian distribution has just flattened. And one that is flattened is less confident in this case here. But then we have our transition, we have our first observation Z1. So the conditional here of P of x1 given our observation actually gives us now a quite reliable estimate, because we see that this purple one here is actually relatively narrow and quite certain about its x1. Because we have now plugged in the evidence and we are more certain. If you now transition from x1 to x2, again, you would probably flatten that curve a little bit. And remember, we're not precisely sure if we are in position Z1, because those Z's are uncertain as well, because our measurement is not certain, but we're overall quite certain, because we see that because we say the sensor noise is 1. If we said the sensor noise was 5, so if sigma z was 5, we'd be super uncertain. And this last Gaussian here would probably be extremely wide. But we say we are obviously uncertain because sigma z is not 0. There's always some uncertainty, but it's 1. And now we have quite a good distribution of where our position x1 could actually be, which we don't know exactly because we cannot see it. We can only take measurements. And this measurement could be from an image. It could be from some other sensor, whatever. So the Kalman filter is a highly generic model. And whether you calculate these measurements from images or not, doesn't matter. It's a highly generic signal processing tool. So this was the Kalman filter for a single dimension, for a single variable x. Before we said our bird's flight actually is more, because we have our 3 positions, or our 3 dimensions, x, y, and z. And it turns out that the Kalman filter can be generalized to multiple dimensions. What we need is now not the normal distribution in 1 dimension, but in multiple dimensions. We have discussed this before. And we can describe, using this normal distribution, we can describe our transition model and our sensor model. Because, again, as before, we are using linear Gaussians, but this time in higher dimensions. And now there are a few new entries, f in sigma. So sigma x is the, or we use this in our linear transition model. We use these matrices to describe our linear transition model and to describe our noise covariance. And H and sigma z are the corresponding matrices for the sensor. So we have the transition as well as the noise. for the transition model. And here we have this for our sensor model and the noise in the sensor. Because the noise before was the sigma, now it's the covariance. And it turns out if you then use this for more than one dimension, so as of 2 dimensions, you can describe your Kalman filter with these 2 key equations. I'm not reading this out. This is something you would be using in a library if you use the Kalman filter for multiple dimensions. But in fact, this is just a generalization of before, because before we've seen how to update the mean and how to update sigma, because we said the mean and the sigma, they just depend on the past mean and the past variances. And in the generalized setting, so as of 2 dimensions, this is all described in some matrix notation. And we have a couple of more, so we have our matrices F, H, sigma X, sigma Z, and we can plug them together in order to describe our mean and covariance update. But I'm leaving this aside. You don't need to know this by heart, but it's just a generalization of before. And the key insight before was this one here, where the new mean and the new variance only depend on the old mean and variance. And this also holds true in the generalized Kalman filter when you work with matrices. And only your task would be, you would define these variances depending on your setting, your sensors. You would define the initial position or the initial values. And then you can use an advanced library, and there are plenty of Python libraries that offer the Kalman filter for you, in fact. There are some more details here in the slides in case you're curious about this general case, but it doesn't matter for now. You can use Kalman filters. It turns also out you can also use Kalman smoothing. So this whole approach in Kalman that we have seen now, because it goes back to Mr. Kalman, in which we use continuous variables, this can also be used for smoothing. So there's also a Kalman smoothing and not just a Kalman filter. Kalman filters can be applied to, in general, continuous state variables and noisy measurements. This has been used in systems in pump mills, in chemical plants, nuclear reactors, even national economies, flying to the moon, or tracking objects in a computer vision setting. So it's a highly generic statistical approach. And my hope for you is that in the future, you're not just applying this in a computer vision setting, but maybe for some totally other learning problems that you're working on, because it's not just vision problems. And maybe some of you will be working on a machine learning system in a chemical plant in order to keep track of the state estimation, and maybe you have some sensors to measure something. You're processing this in a machine learning system, and eventually you're plugging what your machine learning system predicts into some kind of Kalman filter in order to keep track of the dynamical system. Kalman filters are very diverse. We've looked today at Gaussian linear distributions. There are far more extensions. For example, there is the extended Kalman filter, which allows non-linearities. There are switching Kalman filters that run multiple filters in parallel in order to combine their insights. So you have weighted sums of different Kalman filters, and so forth. So there's a huge variety of Kalman filters, which doesn't matter for now. But if you want to see the theory we have discussed today, maybe in a more visual way, there are numerous videos on YouTube that are produced extremely well in order to give you a few visualizations of how the Kalman filter works. Maybe this is helpful for you, maybe not, depending on how you learn. But I think it's important that, first of all, we've discussed the theory. And the key essence you should remember is the Kalman filter allows us to do state estimation, where we have noisy states, noisy measurements, and all the variables are continuous and not discrete. Now, we will now look at another approach to handling image sequences, which is an approach specifically tailored to vision. A Kalman filter, these temporal models we have seen, they're highly generic, can be applied to many problems. What we see now is specifically for vision. And concretely, in a lot of vision applications, we're actually dealing with a problem that's called a correspondence problem. The correspondence problem refers to ascertaining which parts of one image correspond to which parts of another images, where differences are caused by a movement of camera, time has passed, or objects have moved. So time passes, objects move, or the camera moves. And we want to match which parts of an image match to another part of the image that was taken in the other setting. And this correspondence problem is actually probably the case or something you come across in a lot of vision problems. We didn't call it a correspondence problem so far, but we will now look at a few examples where this is actually a case. For example, stereo vision. Stereo vision means you have two images, they are from two cameras at the same time. Stereo vision is in fact something we will discuss a little bit also in the Outlook chapter of more advanced topics. So you have a setting and you have two cameras on the same setting. There is also the optical flow. The optical flow means the flow of time in two images taken from the same camera, for example. There's also cross-scene correspondence, in which images are from two totally different scenes and you may want to match something. And there is also structure from motion and visual SLAM, in which objects are from different but partially overlapping views of scene. SLAM is something we will see in the introduction to mobile robotics. SLAM is the simultaneous localization and mapping, something that allows us to do localization and in a map and mapping of an unknown map at the same time. So this correspondence problem actually appears often in computer vision. And we'll now focus on the optical flow, which describes the flow of time in two images. You need to imagine this as following. We have our image, which is a matrix. So we have dimensions x and y, plus we have time t. And now, from t to t1, some objects are moving. This object is moving to the right, this to the upper right, this lower, and so forth. So it's the motion or apparent motion of objects or surfaces or edges in a visual scene caused by the relative motion between an observer and the scene. And apparent motion can be caused also by lighting changes without actually any motion, but this is something you can think about, and later, or maybe we'll discuss it briefly now. Imagine you have a rotating observer, so maybe something that is moving around an object, in this case a fly. And like this, you can also create apparent motion without, so you can imagine this as a rotating sphere. But probably after we do the optical flow, we can go back to that example, and we will also look at a quick image or a quick visualization of the optical flow. Let's start with a simple example. So we have this scene here, and we see there are football players. They are entering through this gate, and we take an image, and maybe half a second later, we take another image. And we see that there is some motion in the image, or from one image to the other. Concretely, these football players, they're entering, and we could see, well, some pixels that were here are half a second later, or 200 milliseconds, whatever, later over here. This head is moving, the arm is moving, so those pixels are moving from one image to the other. But there are other parts in here where there is very little motion, like those people observing the game. Maybe one is standing up or not, or moving his arm, but there isn't that much motion. And in the cross, there is no motion either, or at least not much motion, maybe very little if there's wind, whatever. So most of the motion is here, and we want to be able to describe this motion by using the optical flow. There are a few assumptions we are making. We are assuming that the brightness is constant. So we look at the projection of the same points and in the same, so the points always have the same brightness in one image or the other. We assume there are small motions and that points move related as their neighbors. Because this point here in the head, in the middle of the head, moves very, very similar to the pixels around it. And the head of this person here moves or the pixel in the center of this head moves probably very similar than the other pixels around it. So these are, and the brightness assumption means that these pixels here have the same brightness once they are moved, or at least more or less the same brightness. In reality, this obviously changes a little bit, but it's an assumption we're making now. And in practice, those assumptions actually work out quite well. I will again switch to my iPad and derive the optical flow equations with you. And then we see what it's actually useful for. So in the optical flow, we want to express the intensity at a pixel as I, as a function of x and y. This is something we had already seen with the Harris corner detector, for example. I. And this time we say this is at time t. And we can say that after some change in time, a small change in time, for example, from one pixel to another, this will look slightly different. We say, well, it's x, y, and t, but we add something on top. We say x plus delta x, y plus delta y, and t plus delta t. And we assume that they are the same now. So this means this is our brightness constancy we assumed before, because we said that pixel, it moves in x, y as the time moves, but its intensity is the same. And if we take now our intensity here from before, we can try to apply the Taylor series here. So Taylor series or Taylor expansion, it's something we had also done in the Harris corner detector. And we will try this out now. So we say Taylor. And then we can describe this term here as I of x, y, and t, plus we have the change of I along x times delta x plus the change, so these are partial derivatives, the change of I along y times delta y plus the change of I, the intensity along t, times delta t, plus obviously higher order terms. Because you can continue this infinitely many times, but we don't care about the higher order terms. Now that we've said we have on the right this updated intensity where some time has passed and the pixel has moved along X and Y, we can on both sides just eliminate the original intensity because we had this equation. So this means here we have a 0. So it's 0 times this one here, because we ignore the higher order terms. And I will write this out again. We say 0, put the 0 to the right later. We say the change of I along X times delta X plus the change of I along Y times delta Y plus the change of T along T is 0. Just a consequence from before, because we said the intensity is equal to this intensity, and we did a Taylor series on the right, and then we could remove these terms. So equals 0. And then we will now divide by delta T. So we divide all of these terms. So this is delta. No, you find this step by step in the slides. I just save some time to write this, but each term is just divided by delta T and still equals to 0. So here we have a delta T divided by delta T. We can just eliminate this. And now we will write this in a simplified way. It's a technique quite similar, or an approach quite similar to what we had done in the Harris corner detector. In Harris corner detector, we didn't work with time, but we had also renamed some variables just to simplify all of this a little bit. So it's the change of I in X. The one that I'm skipping here, I'll write down soon. It's a change of I along Y and the change of I along T. And now I call this Vx and Vy. And Vx and Vi are just the xy components of the velocity or the optical flow of the intensity. And so I'm just renaming those. And we can again rewrite this in the next stage a little bit. We now call this Ix and Iy. Still Vx and Vy. We've also done this in the Harris corner detector, that this part here was called Ix and Iy, just to simplify it a bit. We work with single variables, plus It, and say this is 0. But now I can develop this here in the iPad dynamically. We can also just say this is, we subtract on both sides IT, or minus IT over here, because we've just subtracted this on both sides. The minus should look a little bit nicer, like this. And we can again rewrite this as nabla I, which is the gradient, times V. And V is a vector, so it's in bold, is equal to minus IT. So you remember the gradient of I. The gradient is a vector of the partial derivatives. We have these partial derivatives here. And v is the vector of vx and vy. So I'm just putting in some arrows that you see where all of this moves. And here we have this. So nabla I is just a gradient of I, so the partial derivative along x and y, and v is just a vector of vx and vy. And if you multiply this gradient, which is a vector, and the other vector, you just get the scalar product. So it's just a simplification. The problem in all of this is minus it. The problem is that this equation has two unknowns, and it cannot be solved as such. Because we only have one equation, but these two unknowns. So it doesn't work. And this leads to a consequence, which we call the aperture problem. I just need a second to open this in my browser and then show you what the aperture problem looks like. Just need a quick second to open this because we need a visualization of the aperture problem. So zoom in. This is the aperture, or here in motion prediction, the aperture problem. And if we see something like this, we have something behind this hole. We have a small hole to peak. And in fact, this appears that whatever is behind with this pattern is moving down and to the right. Maybe send me a thumbs up if you agree that this looks like that whatever is behind there is moving down and to the right. If you think you see that, or you could imagine this. If you don't see this or you see a different movement, maybe a thumbs down. In fact, what we see there could be moving in many other directions. For example, only down or only to the right. So it's impossible to determine unless the ends of those bars become visible through this hole, which is the aperture. And we have this aperture problem, and this aperture problem leads to that our optical flow equation so far doesn't work. So we need to make some conditions or some assumptions about the optical flow, so how those pixels are moving in our image. And in my slides, there is a further reading which actually shows you multiple optical flows or multiple approaches to optical flow. Feel free to open that site on NanoNets, and down there you see the optical flow problem again, and you see certain concrete implementations. So this is just the optical flow. It's just the equation we just seen, just use a different delta, but fine. This is what we had just done. And then there are concrete implementations that make a concrete assumption on your setting, because so far the equation we have defined is not solvable, and we have the aperture problem. And there are multiple approaches of how to address this. This is your homework for next week. And what you see in there in one of the subsections is a corner detector, which selects pixels to track. And internally, it also uses the Harris corner detector. And the Harris corner detector is something we saw a few weeks ago. So this may be a revision of that. And there are other optical flow implementations that make other assumptions for other use cases. And then that equation actually becomes solvable. This is referred to in my slides. So in my slides, I have the aperture problem, but the aperture problem is not visualized here, or it's not dynamic. That's why I opened it. You find a link here, and you can check this NanoNets block in order to learn more about concrete optical flow methods. So I know the image sequence processing chapter was not easy, especially the Kalman filter is tough, but you saw that Kalman filter can actually be derived step by step because we've started with these highly generic temporal models. That's what you just did. And temporal models can be used for many different applications, and the Kalman filter makes a couple of assumptions. Remember, noise in the measurements, and we have continuous variables. And eventually, deriving a Kalman filter is not that difficult because it just falls off from these temporal models. And you have different sensor inputs, and the camera or something you have found in the camera could be your input. And you can use this for far more than just vision problems. We've seen the correspondence problem and the optical flow. Now we have 2 chapters left. And next week, we'll discuss mobile robotics because there's not enough time to start discussing this now. But there is a last chapter in the slide deck, which is called Outlook. It's just an outlook to discuss some far more advanced topics or topics that are hot right now. So I want to take the last time or the last few half hour or something, last few minutes, half an hour to talk with you about this. And then next week, we will look into the foundations of mobile robotics, which some of you may need for their mobile robots. I'm curious, who of you has got or got a mobile robot last week from our lab assistant? If you have, maybe green sticker, thumbs up, something like this, that I see who actually got a robot. Maybe had some time to already play with the robot and set it up. For any technical questions, Mr. Rankel is at your disposal. You know his contact because you were able to pick up the robots. And next week, we'll discuss the foundation of mobile robotics in case you need this for your projects. And next week, I also say more about the projects. And now we'll look in the Outlook chapter. There are a few more topics that could be helpful or interesting maybe for some of your projects, or they are maybe for some of you just too advanced, which is also okay, because your projects can cover whatever is related to vision, but maybe some of you want to take an extra mile and work on even more advanced topics. One more advanced topic is 3D vision, because when we looked at in the first lecture what computer vision is, we're dealing with extremely complex inverse problems, and we're dealing with under-constrained ones because we have a 3D world and we map this to a 2D projection. And that's why we lose some information. But a consequence could be that big distance objects appear small size as small size objects. So inferring distance from the camera just with a single image is tricky. But for a lot of real-world problems, we may, or for some real-world problems, we may want to deal with 3D vision. And concrete tasks could be, for example, a 3D reconstruction of images or from multiple images. So we take multiple images of the same object, multiple scene, and we may wish to have a 3D reconstruction. Maybe we want to localize something, but just its distance is hard to infer from a single image. Maybe we have a robot driving around and taking multiple images, and like this, we may be able to infer some location or something that is away. There's also depth estimation. Depth estimation means we have an image, and in the image, we want to determine how far a pixel is away. So we have a pixel, and the pixel refers to an object or a part of an object. And I want to know how far is what I see in this pixel, how far is that away? And this can be, for example, addressed from a stereo vision approach. In a stereo vision approach, so we have a scene here, we have these two spheres, and we have two cameras. And we see how these cameras, or what these cameras see. This camera here sees something, and we see that the green ball is in front of the orange ball. But this camera sees something different. It sees the orange one, which is here, and to its right is the green one. So with these two cameras, we actually learn much more about the scene than just with a single camera, because it allows us to actually examine the relative positions of objects in these two, or in this scene. There is plenty of mathematics that you can apply to stereo vision. With these two cameras and so-called epipolar geometry, you can actually use geometry and determine how far objects are away from these cameras, because you have two. And we as humans, we have two cameras, we have two eyes, and that's why we're very good in working in 3D settings, because we can estimate distance quite well, because we have two cameras and our brain got trained over the years very well. Epipolar geometry isn't that difficult, but it's quite a topic that takes some time to discuss. In recent years, neural networks have also made approaches or have made progress in 3D vision. For example, if you have an image and you want to know how far is the object in a certain pixel away, you can train a neural network on some tasks. So your training data would be the pixel image, and then not a label, but rather you have a label for each pixel, and that label would be the distance. And this is maybe something you have measured experimentally in a controlled setting, or you use a sonar or some other device to give you these values. And then you're training the neural network on the image and on many labels, because you have one label per pixel. And you're training your neural network, so for example, a convolutional neural network, on many of such input pairs. The pixel image as well as a matrix with the labels, which are the distance. And it turns out, like this, nowadays, you can estimate depth quite well, just with a single camera that was, and you have a neural network that was trained on a lot of such images with those labels in a matrix form. And then for new settings, this works actually quite okay. Maybe not as good as if you have multiple cameras, but if you just have a single camera, depth estimation with neural networks works nowadays quite well. If you want to learn more about depth estimation, I've also put a link here to a Towards Data Science article, which provides an introduction to depth estimation. I don't remember that anyone in the computer vision project so far has, in the last few years, has approached depth estimation from such images, like using epipolar geometry and neural networks. Maybe this is something someone wants to investigate this year in a project, because I haven't seen such projects before in this course. I've also worked on 3D vision. I published a paper a few years ago about 3D vision. And what we did, in fact, was a paper here. It's called Using Augmented Reality and Machine Learning in Radiology. We published this as a book chapter. What we had were CT images, so computed tomography images of organs like a liver, but also of the whole torso of a human. And these are 3D images. They come from they are computed tomography images. And in this torso, if you look in deeper, there are organs. And now radiologists, they spend a lot of time on segmenting these objects. So they click into the images, they have screens, and they try to go through this 3D image on their screen and then somehow set markers in order to segment organs or maybe lesions or other damages. And we felt that that doesn't work too well, so we built a machine learning system that could do this. Others have done this before, but I think we built a better approach at that time in order to do something like this. And like this, we were able to automatically segment images. We've used a neural network that others have built before, but we enriched our methodology. And then we were able to detect or automatically segment organs, lesions, and other problems that may be on the organ. But then again, you need to visualize it. And visualizing 3D data on a 2D screen is not too great. So in that time, so this was maybe 6 years, 7 years ago, we visualized this in a Microsoft HoloLens, and then doctors could actually, you know, see that sort of holocron and walk around it, which is far more intuitive than looking on that at a screen, but rather if you see it in somewhat 3D, you can walk around it. You can maybe touch it with your hand and turn it. It's far more intuitive. A few months ago, I used these new Apple glasses that are available, this augmented reality device by Apple, which is terrific. I don't know if you had a chance to try it yet. I tried it a few months ago, quite some progress from the first Microsoft HoloLens a few years ago. If you're curious about the methodology we have taken and the neural network and how we process this 3D image in order to segment, it's described in detail in this book chapter. It's also available in our Nextcloud directory. Now, this is some of my work I have done on 3D vision with others. Then a different kind of neural network has become more popular in the last few years, so-called GANs, or generative adversarial networks. It looks something like this. In fact, it's actually two neural networks. You have a generator and you have a discriminator. And what this kind of neural network aims at is you have real data, for example, real images, but you can also apply this to totally different data. And you have your real data and you have samples of that. And you also have a generator, and the generator will also generate samples like images, but fake ones. And then you're training this neural network to generate fake images. And your discriminator is your second neural network. And that discriminator is supposed to distinguish between real and fake. And these two neural networks, so the generative adversarial network is actually, it's two neural networks, the discriminator and the generator. They are coupled, and you're actually addressing a game theoretic problem because they both try to get better at the same time. The generator tries to fool the discriminator and is being trained, but the discriminator should also get better, distinguish between real and fake. And it turns out that this kind of approach, a generative adversarial network, became very popular a couple of years ago to build better neural networks. And as a byproduct, you can use them to generate more fakes, for example. And maybe 4 or 5 years ago, you saw all these funny or fun apps come up that you can run on your phone, in which you put a photo of yourself, and then you can change your pose, your age, your expression. You can make yourself younger, older, smiling, not smiling. And I don't know if you have used such apps, maybe thumbs up, thumbs down, if you have used such apps that make you older or younger or change your pose or whatever. And they are typically, or they were typically built at that time on top of generative adversarial networks. While you see all these examples of generative adversarial networks for images, you can use them for many other things and not just images. You can use this for sensor data to generate more sensor data and so forth. So it helps you maybe if you have a reduced training set to generate more data samples for your actual training. So these generative adversarial networks, they have become quite popular with lots of applications in vision, but lots of other applications in other domains as well. I don't remember that a lot of groups have used them in their past projects because it's, again, a more advanced topic. Some groups, I think, did, but this is also something that you could investigate further in your projects. Now, the vision transformers have become more popular, and in order for us to look at vision transformers, in order to train them, we need an approach that is called self-supervised learning. So when you have an introduction to machine learning, you learn that there is supervised learning, that there is unsupervised learning, and that there's reinforcement learning, which are the three pillars of machine learning. But over the last few years, a new approach that we call self-supervised learning has become more popular. And self-supervised learning is explained in a YouTube video in detail that I think explains it extremely well. So you're most welcome to watch it. But what that approach allows us is, because for supervised learning, we will always have a limited amount of data. And self-supervised learning allows us to take advantage of certain structures in the data in order to learn better patterns. How it works exactly is described in, for example, this video, but I'll provide a few more explanations now when we look into vision transformers. So transformers are a kind of neural network that goes back to initially text problems. And like ChatGPT is something I discuss in greater detail in my big data course. And ChatGPT stands for chat and then generative pre-trained transformer. So it's a generative model, it's a transformer, which is a kind of neural network, and it's pre-trained, so it was trained on large amounts of data. And this kind of architecture is something that was proposed, I think, 6.5 years ago or something like this. And over the years, it was not just used to generate text, but so-called vision transformers are an adoption that work well for generating images. And if you have a prompt, you can generate images, something like this. My prompt is, I want a robot or a painting of a robot that draws a painting, and I want a green background and blue water, whatever, and I want this as some, painting style. And you write a prompt, and then the vision transformer generates you an image for that. While I keep talking, maybe you can share some insights in the chat what you are using vision transformers for. So what kind of images you have been generating in the last few years from prompts, for example, using DALL-E or other tools. Because there is a question of how does this affect the jobs market? Yes, maybe artists can be replaced to some extent in marketing, but you can also use this, for example, if you're a furniture designer at IKEA and you're given the task of designing new chairs that look like an avocado. It's maybe something that isn't that obvious for a typical furniture designer, but you can just type a prompt. Show me chairs or couches or whatever that look like an avocado, and suddenly it's generated purely from data. Not all of these chairs are so comfortable, but maybe some of them are quite useful. And then the furniture designer would take them and amend them and actually come to a good product. And again, maybe send me some comments here in the chat what you have used vision transformers for, or maybe thumbs up, you have ever used a vision transformer to generate images, or thumbs down, you have not used that so far. Because for example, for ChatGPT, you can use DALL-E to do this, but you need a subscription. I have this subscription. I find DALL-E plus the other known or well-known models quite useful, especially if I need some new figures for slides. Sometimes I generate them just using DALL-E, not too much for this course because I use the figures from textbooks or something. But if you need something a little bit artistic or something, maybe for a social media post or in order to visualize something, DALL-E and others like Stable Diffusion and so forth can be quite helpful. Some of you had some thumbs up, so maybe you can send in the chat what you have used these vision transformers for. And I said all of this goes back to a paper from maybe like 6.5 or 7 years ago, which was called Attention is All You Need. And it initially targeted natural language processing problems, text problems, because if you look at earlier text generators or chatbots or assistant systems in general, what they internally often use to understand human language was, for example, a hidden Markov model. We've talked about hidden Markov models earlier today. It's a temporal model, works a little bit like the Kalman filter, yet different because it assumes discrete states. And this was often used for natural language processing problems, like speech recognition or understanding something in text and so forth. Whatever model you apply, one of the challenges that you're facing is you need to figure out how words correlate. Technically speaking, it's not words, it's tokens. A token can be a small word, part of a big word, or some other special character. And you need to learn from large text how these tokens correlate. So you're, in fact, learning some high-dimensional probability distribution of how tokens correlate. And this was done with many approaches, and now then it was discovered that these vision transformers, they do this particularly well. That transformer models did this particularly well. And these transformers, they are neural networks that internally use the so-called attention mechanism. That attention mechanism is something that is trained from self-supervised learning, and it allows us to understand or learn well how tokens correlate. If you want to know how this works, we discuss it a bit more in my big data course, but if you're curious, read this paper. Attention is all you need if you have not read it so far. And then a few years ago, it was noticed that this transformer architecture can be applied to more than text. For example, vision problems. And transformers are now seen as a sort of, I don't know, competitor of convolutional neural networks. Some people have already argued a few years ago that convolutional neural networks would disappear. We would only be doing transformers. I have to say I have my doubts about if vision transformers would fully replace convolutional neural networks, because convolutional neural networks, they have demonstrated extremely good performance in lots of different problems for the last, 30 or 40 years. Transformers are probably good for or vision transformers are good for certain problems, like generating an image out of text or understanding an image and maybe generating a description. But if you want to train these very large transformers, you need a lot of resources, and maybe you don't have those resources and you can do this much cheaper through a convolutional neural network. So that's why I think these two models or two architectures largely address different problems. So far, convolutional neural networks are still used for most of vision problems. Maybe vision transformers are becoming more popular. It's something I'm monitoring, and maybe the computer vision lecture in 3 or 4 years will largely cover transformers and less convolutional neural networks. I don't know. I'm observing the market and see what will happen. If you are curious about vision transformers, this is explained well in this new Bishop book, the deep learning book by Chris Bishop and his son. I talked about this book briefly in the first lecture when I talked about the bibliography. The book is available on the market, and it provides a few pages, or I don't know, half a chapter or something, that discusses vision transformers extremely well. In order to understand this, you need a background in neural networks and in transformers. it's a lot of details that I'm unable to discuss in the computer vision course, so it's more of an advanced topic. If you're curious, feel free to read the Bishop book. I think it's probably the most up-to-date, well-known vision textbook now on the market for deep learning and covers those things well. There's a comparison between vision transformers and convolutional neural networks. As I've already talked about this, the vision transformer is a completely different architectural design than convolutional neural networks. And a convolutional neural network has lots of inductive biases you're making about the data, like the spatial arrangement and all these other properties we discussed when we introduced convolutional neural networks. Those biases are not really in a vision transformer, rather such feature detectors would be learned much more freely with less constraints, but you probably need more data and more computing power. And for a lot of vision problems, probably the inductive biases the convolutional neural network makes are quite reasonable. There are also some combinations that have been proposed over the years, like how to combine a neural network, convolutional neural network, and a vision transformer, or how to add self-supervised learning to convolutional neural networks. There are such hybrid architectures. We'll see in the future how they develop in the long term. Maybe some of you want to use vision transformers in your projects. You're also most welcome to do this. If you need computing power, we have our deep learning lab available. If you want to use some of the GPUs or other infrastructure there, feel free to talk to Mr. Runkel. He'll be happy to provide you with more computing resources. Yet the vision transformers topic is probably one of the more advanced ones. I'm aware that others of you may rather work on some of the other topics. Next week's lecture will cover the foundations of mobile robotics. I'll also say a few words about the projects next week. And next week's lecture will be recorded because there will be some general information. First of all, the foundations of mobile robotics will be taught, and I'll also discuss some more general things about the projects. All of this will be recorded. But when you give your project proposal presentation in a few weeks, we're not recording this. That's important. We will also only discuss my content, not your proposal presentations. So next week will still be recorded. And next week, I'll also say a few more words about an upcoming guest lecture in a couple of weeks and so forth. And next week, we finish the lecture content, and then we're moving to a guest lecture and then to the project phase. And I'll provide more information next week. So we're done for now. I didn't see any other questions here in the chat. I wish you a good afternoon, and I look forward to seeing you in next week's lecture. Take care. Bye-bye.